Hello, so today we are going to do this problem called max number of k-sum pairs. It's part of Leetcode May challenge. So the problem says we get a number array and we get an integer k. And what we want is to pick two numbers that have a sum equal to k and remove them from the array. And we want to try to do that as much as we can, and then return how many, what's the maximum number of operation we can do. And the definition of an operation is picking two numbers that equal to k and removing them. Okay, so if we take an example of this array and k equal to 5, we can take maybe 1 and 4 first, right? So we take these two, remove them, those equal to 5, so that's operation 1. And then we take these two, 2 and 3 as well. So that's the second one. The array is empty, so we are done, and so we return 2. If we take a look at the second example, k equal to 6, well, we can take two 3's, so this one and this one, but we can't do another 6, right? And so the value is just one operation. So that's kind of the goal. If we take a look here, these are the bounds. This tells us that sorting should be possible, but we shouldn't do something that iterates over k, over from 1 to k, for example, because k can be really high. So that's the problem. Now let's see how we can solve it. So the simplest idea that we can start with is similar to the two-sum problem, where basically we look for the complement. So what this would mean is that essentially we can traverse the array, right? And then as we go, we count the occurrences of the numbers that we've seen so far. And then for each number, we check if the complement, if we've seen the complement before. If we did, we add it to the number of operation, because we can take that number and the complement we've seen before. And that's pretty much it, right? So very simple idea. Just we iterate, we keep we count the occurrence as we traverse. So we count the occurrences as we traverse, and for each number, just check if we've seen the complement before. So very straightforward there. Now let's code it up. So what we can do is we need a map that stores the complements that we've seen before. So we just we can call it occurrences, and so it's part of collections. We need to get a dictionary, and we can initialize it to integer so that initially it's the number of occurrence is 0 for numbers that don't exist, and we can go through the array. The other thing is we need to have a counter for our operations, and as we said, we need to look for the complement for each number. So the complement in this case, basically the number plus some x value is equal to k. So what this would mean is that x is just this. So this is what we will be looking for. This is what we call the complement here. And so k minus num, that's what we are looking for. So if it exists, which means the number of its occurrence is bigger than 0, that means we can take that. So we can pair, so this basically means we can pair num and k minus num together. And so if we do that, then we increase the number of operations. But also, since we paired one of these occurrences with this number, we need to say that number k minus nums, we already used 1, so we need to subtract it, right? Otherwise, which means there is no complement, we need to store that we've seen this number, so that if, let's say, k equal to 3, and we've seen 2, we need to store that we've seen 2, so that if we see 1, we can count those two as a pair equal to 3, right? And so here we need to say occurrence of num plus 1. Notice we didn't do it here, right? Because we've used the number here. We already used it, so no need to add it. And now at the end we can just return the number of operations. And that should be it. So let's run this. Okay, cool. So we can submit. And that passes test cases. Now, in terms of time complexity, this here is oven, right? Because we are going through the array. And then in terms of space, we are using this extra map that will contain at most n elements. So also oven, time, and space. Okay, so that's the solution using Hashtable. We can also use one idea, which is that for each number x, for example, the number of possible operation is actually, so if we have a number for the numbers in the array for a number x, the number of operations that x can be in is basically the count of x in number, the minimum of the count of x, and the count of x minus k, of course in nums. So something like this, the count of occurrences for x minus k, sorry, for k minus x and for x. That's basically the minimum number of operation x is involved in, because we pair x with k minus x, but the minimum number of occurrence, that's what the number of operation we can do, because if x occurs 3 times but k minus x occurs only 2 times, we can pair only 2. We can do only 2 pairings, so we can do only 2 operations. So that's the idea here. However, if we add 2 here, since if we traverse the nums and add 2, let's say for example k is equal to 5 and num is equal to 2, right? So we are looking for k minus nums, which is 3, right? But we'll count it twice. We'll count for 2 and we'll count for 3. And so we need to divide the overall count by 2 so that we take into account our double counting, right? And so that's pretty much it. So since we are using count, we can just in Python use counter to have a map that gives us the count directly instead of counting every time, right? And so here we can traverse the numbers, and what we'll do basically is, as we said, we need to add 2 operations, the minimum of the number of occurrences of x, right? So number of occurrences of x, let's name this x, and the number of occurrences of k minus x, right? And that's the number of operations. However, since we are double counting, we are counting for x and we are counting when we reach k minus x in the array, so we need to divide by 2, right? And that's pretty much it. However, counter here, we need to pass the array. And so let's run this. Okay, so it looks like there is, sorry, yeah, here we need to go through the occurrences, right? Because otherwise, if let's say number 2 occurs 2 times, then we will count twice x, right? So we want to use occurrence here so that it's unique. Okay, so let's submit. And this passes test cases. Okay, so this solution using counter in terms of time complexity, we are using just one loop here over occurrences, which is at most has a size of n, so it's over n. In terms of space complexity, we are using occurrences, which is also of size n at most, so it's over n. Now, we can solve this differently if we don't use, if we want to reduce the space complexity here. We can sort it we can do it slightly differently. So how can we do that? So the trade-off, of course, would be time complexity, but we can solve the array. Once we solve the array, then the idea is to have 2 pointers, one at the start and one at the end. And if the sum is equal of the start and end is equal to k, we count it. But if it's bigger, then we can move the end to the left, right, to decrease the sum so that we can have a possibility of reaching k, right? So what I mean by that, if we take the example here, let's take maybe this one. So what we can do is basically put the start pointer here and then put the end pointer somewhere here, right? And so we sum this, so our k in this example is equal to, if we take a look here, it's equal to 5, right? So basically we do, we start with s at the start and end at the end, right? And so 1 plus 4 equal to 5, so we add that to our operations. And then we advance our both pointers. Advancing the end means going backwards, right? And advancing the start means going, let me just do this. And advancing the start means going forward, right? And so now we have 2 and 3. It's equal to 5 as well, so we increase our operations. And then we advance this. But now we hit our condition, which is s should be less than n, right? Because we are done at this point. We considered all pairings. Now, what if we have? What if the sum is bigger than k? If the sum is bigger than k, that means since the end is for the end here, the numbers that we visited before are bigger, so as we advance our end pointer, which is going backward, we will get a smaller values. So if the sum is bigger than k, we can just decrement the end to possibly have a smaller sum and get a number that is equal to k. But if it's smaller, right, then that means we need to advance s, because then we will get bigger numbers and get a chance to reach k, right? And so if it's basically what this would mean, if the sum is bigger than k, then we decrement the end, and then if the sum is smaller than k, we increment the start. Because if we increment the start, we will get a bigger sum, and so we have a higher possibility of reaching k. But if it's bigger, there is no use in incrementing s, because then we'll get a bigger number. But we already have a number that is bigger than k. So that's the idea. So let's do that. So it's sort of 2 pointers, because we have these 2 pointers that advance, and then we sort also initially so that we can take advantage of this property, right? Okay, so let's sort here. So first we need to sort our numbers. Then we need to declare our 2 pointers. Start at the end, and start at 0, and end starts at the end of the array. And then we need the number of operations, start equal to 0, and then we can keep going until these two meet, s and n pointers meet. Now we check if the sum is equal to k. That means we already have what we are looking for, so we increase the number of operations. However, if this sum here is smaller than k, or if it's bigger than k, that means we need to move our end pointer, so we decrease it. Otherwise, it means it's smaller than k, so we move our start pointer by increasing it. And then at the end, we just return the number of operations, okay? And then we can run this. Okay, so it looks like, yeah, so one thing here is when the sum is equal, right? We already considered start and then end, so we need to move these pointers. Sorry about that. So we need to move both pointers here. Okay, let's move. Okay, let's submit. Sorry. Okay, so that passes test cases. So in terms of time complexity for this solution here, so this is, we are sorting first, right? And then we are doing progressing here, and this is at most the number of elements of the array, because each time we increment one of the pointers. So overall, it's O n log n because of sorting, plus O n, but since n log n is bigger, we just asymptotically bigger, we just use O n log n. In terms of space complexity, this is where we improve on the previous solution, it's O1. Okay, yeah, so that's pretty much it. Now, one simple modification we can do to this one to make it better is that Well, let's say our k value is equal to maybe 2, right? And then we have our end pointer maybe here, right? And then our start pointer is at 3, right? So here, there is no need to keep going, right? Okay, maybe we have more elements here. Let's just suppose we have more elements here, right? And this somewhere here, right? So k is bigger than 3. As we advance, we only will get bigger numbers, right? So we will only have a sum that is bigger than k, because numbers are always positive right here. And so there is no need to keep going. We can stop right there, right? Because we will never get a sum that is equal to k, because the number at the s pointer will only get bigger, right? So the optimization we can do here is we need to keep going only while this is less than k, right? Also, if it's equal to k, let's say 2 here, right? We will only get bigger numbers, right? And 2, you can't pair it with anything else to get k except 0, but we know because end is after s, we won't have 0, right? So that's why also it's not small or equal. One thing you may ask is, okay, can we do something for e to control it, maybe also while this is smaller than k? But we can't do that because we know we sorted the array, right? And so as we move the end, the elements get smaller. So if the number was bigger than k, as we move e, we have a chance of getting a smaller sum, so we have a chance of reaching k. So we can't do the same thing for end. Yeah, so that's pretty much the optimization here. So let's just run it, make sure it works. And if we submit, okay, so that passes test cases. Yeah, so I think that's pretty, yeah, one thing to note is this is same time and space complexity. Slightly optimized, but same complexity. Yeah, so that's pretty much it for this problem. Thanks for watching and see you on the next one. Bye.